Hello, this is the first part of the first session of our course on differential geometry. So in this course, the main topic of study is kind of smooth manifold. Here, we will be mainly studying smooth manifolds. So what do I mean by a smooth manifold? These are kind of geometric shapes, geometric objects, loosely speaking. So geometric objects that if you look at small piece of them, well, the technical word is locally. They really are similar to Euclidean spaces, right? By Euclidean space, I mean something like R or R2 or R3, etc. So locally, they are very similar to some Rn for some kind of positive integer n. So let's look at one example. Maybe one of the simplest examples to consider is just a circle. Think about the smooth circle in a plane. This is a manifold. Why is that? Well, any point x you pick on this circle, if you look at a very small neighborhood around that, this red thing, this kind of looks like an open interval inside R. So it locally looks like a bit of R or R1. Since every point has this property, I would say this circle is a one-dimensional smooth manifold, or simply just one manifold, smooth one manifold, right? Now, knowing that circles are manifold, well, essentially, as I said, this means locally they look like R. It's good to notice that globally, that's not the case. Globally, a manifold can be very different compared to Euclidean space. Globally, a circle does not look like R. Okay, let's look at another example, figure 8, which by that I mean this curve which has a self-intersection point, the one-dimensional thing. So if we pick any generic point x, again, if you look at the small neighborhood around that, that neighborhood looks like an interval inside R. So you might wonder if it's a one-dimensional manifold or not. But if you pick Y to be this intersection point, the small neighborhood around Y looks like this cross. It's like union of two intervals. And this is not similar to an interval inside R, right? That's why we say figure 8 is not a manifold. So this is not an example of a manifold or smooth manifold. In fact, this point y is kind of a singular point. Now, let's go one dimension higher. Let's go and look at two-dimensional examples. Think about the surface of the Earth, just the surface, not the solid object, not the interior, just like surface of a balloon or surface of a ball. This is a two-dimensional manifold. Any point x you pick on the surface, you can see a small neighborhood around that point x, kind of look like a kind of small open subset of R2, right? Since this is the case for every point x on this sphere, we would say this sphere is a two-dimensional manifold. Another example would be surface of a donut, right? There is a hole there. Again, we're assuming this is not solid, this is not field, just surface. Any point x we pick, the small neighborhood of x, again, looks like an open subset inside R2, right? And this holds for any point, even if we pick x, I don't know, maybe at an interior point, which kind of might look more complicated. This doesn't matter. Any point we pick, it always has a similar neighborhood. Okay. Now, let's look at another example which is not a manifold. Think about cone. This is the shape which in math we call it cone over a circle. Non-mathematicians might think about it as the union of two cones intersecting at a point, but the whole thing in math literature is called a cone. If you pick a generic point like y, you would see a small neighborhood of that. Again, looks like an open disk inside R2, so it might be tempting to say this is a manifold. But if you look at the point x, it is again a point of singularity in the sense that if you look at the small neighborhood around x, what we would get is this shape, which again looks like another cone. And it is not similar to an open neighborhood in R2. We can prove this a bit more rigorously later, but just on the intuitive level, this seems kind of clear. So this is not a manifold, again, because x is a point of singularity. So this cone is not a manifold. Okay. So let's, well, just as a remark, we can kind of go to higher dimensions. We can think about three-dimensional manifolds, four-dimensional manifolds. For any positive integer, we can think about n-dimensional manifolds. They are more complicated to imagine, but we would get there. So now let's define what do we mean by smooth manifold more rigorously. I would say M is a smooth manifold. So this is my definition, right? What do I mean by smooth manifold? If M is a topological space with some extra structure, so I should have an atlas on M. What do I mean by atlas? It's a kind of set or collection of pairs, U alpha and phi alpha, where U alpha with some index at alpha, where U alpha is an open subset inside M, so U alpha is open, and we have this property. So the union of all these U alphas would be equal to M. This means they cover M, or they form a covering for M. You cover your topological space with a collection of open sets. And then for any alpha, the map phi alpha is a map from U alpha to Rn, or to an open subset of Rn. This is what we mean by locally looks like a Euclidean space. So there is a map which takes U alpha to some open subset of Rn. Let's just denote that V alpha to be the image of phi alpha. This map is expected to have a few properties. So first, it should be injective. And of course, it's surjective onto its image, so it's one-to-one. Moreover, I want this map to be continuous, right? And I want its inverse, which has inverse on phi alpha because it's one-to-one. Its inverse, I want it to be continuous too. So, I mean, in topology, we call these maps homeomorphisms, right? One-to-one continuous with continuous inverse is called homeomorphism. So we have a collection of homeomorphisms. Kind of locally, each open set is homeomorphic to an open subset in Rn. What do we mean by smooth? There is an extra property. So let's schematically say this is our manifold M. Let's pick two of these open sets. Let's say this is U alpha. Let's say we have another U beta, say this one. And let's say they have non-trivial intersection. Okay, let's say U alpha intersection U beta is non-empty. Okay. Now, if we have that, for U alpha, just by definition, there should be a map phi alpha to some open subset in Rn, right? Let's say to some V alpha inside Rn. And for U beta, we should have another map phi beta to some other open subset of Rn, right? Let's denote that with V beta inside Rn. Now look at this blue intersection. If you look at this intersection through phi alpha, let's just denote this intersection with U alpha beta, which is U alpha intersection U beta. This U alpha beta through the map phi alpha would go to a subset of Rn, right? This blue one, let's denote that with W alpha. And through the other map phi beta, it would go to another open subset of Rn. Let's denote that with W beta. Now we can compose these maps to send W alpha to W beta. First, we go back along W alpha. It's like W alpha inverse. And then we apply phi beta. So phi beta or phi alpha inverse is a map from W alpha to W beta. So I would say my manifold is smooth if all these compositions are smooth, right? That's the last part of the definition. Okay, now there are a few things to note that. First of all, first remark, it kind of makes sense to say these maps are smooth or not. Why is that? This composition of phi beta and phi alpha inverse is defined on W alpha, which is an open subset of Rn, and the range, the target, is also a subset of Rn. And we know what it means for a map from an open subset of Rn to Rn to be smooth. Smoothness makes sense, exactly in the same sense as we learned it in calculus, right? We would say a map from Rn to Rn or Rm is smooth if it has all the higher derivatives, all the derivatives exist, right? So we know what it means for these maps to be smooth. The other thing to note that is that when we are looking at phi alpha, these are they're called local coordinates. Why is that? You know, when we think about our manifold, let's say again schematically, this is our manifold, we pick an open subset U alpha, and then we have this phi alpha to Rn, right? Now the point is that any point on the manifold is covered by at least one of these open sets. So let's say we have a point x. If I look at the image of x in Rn, phi alpha of x is a point in Rn, so it's given by n tuple of points, x1 to xn. I can call that a local coordinate for x. You know, it's like saying x1 to xn is the coordinate of x. This is defined locally, right? In general, you cannot have a global kind of coordinate, but locally we can do this. So these are local coordinates for x. The other remark, the other important point is that assuming our manifold as a topological space is a connected space, it just has one connected component, it's not the union of different connected components. This number n, which appears in Rn, is well defined, it's fixed. It can't be that some U alpha goes to some open subset of Rn, homeomorphic to some open subset, some U beta to some other Rm. N is fixed, it's called the dimension of the manifold, right? We proved that later more rigorously. Okay, so now think about maps between manifolds. Let's say we have M1 and M2. These are smooth manifolds. We have two smooth manifolds. M2 is also a smooth manifold. I would say a map from M1 to M2 is a smooth map if the following holds. You see, let's say it's smooth at a given point x in M1 if the following holds. You see, we know what it means for maps to be smooth when the domain and target are in Euclidean spaces. We still don't know what it means for maps to be smooth between manifolds. Let's say we pick some U alpha open subset in M1 that covers X. And let's say we pick some open subset V beta in M2 that covers the image of X, Fx, right? So U alpha with phi alpha goes to Rn, V beta with, say, psi beta goes to some other space, let's say Rm. I mean, the dimension of domain and target might be different, right? Okay. Now we can kind of construct this composition. We first can start from Rn. We can go back using phi alpha inverse, then compose that with the map F, and then compose that with psi beta. This map is a map between Euclidean spaces or open subsets of Euclidean spaces. I would say F is smooth if this composition is smooth for some local open subsets. And note that this notion is well defined. It could be that around X, one could, instead of U alpha, take another open subset covering X, right? It's not unique. Let's say it could be that we have U gamma and some other phi gamma, or around f of x, one could take another open subset, be theta in the atlas, kind of the compatibility condition we had in the definition of smoothness of the manifold. Means it doesn't matter which choice you pick. It's well defined. If you check this with respect to one covering, it would be correct with respect to any other. Okay. Now, the next point to consider is that we learned that, well, circle, we discussed circle is a smooth manifold. Let's see that more rigorously. So one way to define circle is as the set of points in R2 where x squared plus y squared equals 1, right, as a subset of R2. So in order to prove it's a smooth manifold, well, we know it's a topological space, I should present an atlas, a collection of open sets that covers the circle, right? There are different ways to do this. I would do this using 4 open subset U1, the red piece. So U1 is the set of points in the circle. We denote the circle by S1. This is kind of notation. I will discuss this later, where Y is positive. I define U2 to be the set of points in the circle where Y is negative. So it would be this, this other subset of the circle, kind of the blue one. This is U2. Note that there are 2 points which U1 and U2 are missing. These 2 orange points. They're not neither in U1 nor in U2. So we should introduce 2 other kind of subsets. Well, that's what I'm going to do. U3 and U4 to cover everything. Okay, this is not unique. This is how I'm picking my atlas. So define U3 to be the set of points in circle where x is positive, and U4, this green part of the circle, where the set of points were set of points x and y in S1, where x is negative. Great. Now we cover the whole circle, right? Now I should define maps phi1, phi2, phi3, etc. to open subsets of R, like homeomorphisms to open subset of R. I define phi1 of x and y, so it should be defined on U1. So let's say what is the value on some point x, y like this. I define it to be x. So phi1 of U1 would be an open subset of R, right? It would be the open interval from -1 to +1 inside R. This is a homeomorphism between U1 and the open interval. I define phi2 in a similar way. Phi3 sends x, y to y. It means if you pick any point here, let's say in U3, the orange one, it's kind of like the projection to the value of y. I define phi4 in a similar fashion. So you can see these kind of give us homeomorphisms on these sets, and you can see anytime kind of we have intersections, this phi o, phi j inverse, they are all smooth maps. So that's a proof that S1 is a smooth one manifold. One could pick different atlas and different maps. This is just one way to do it. Okay, so earlier we mentioned this figure 8 is not a manifold. Let's kind of go over that example more explicitly. Now that we know what is definition of manifold, look at this intersection point. An open subset, very small open subset covering this would be like this cross. It would have been a manifold if this cross was homeomorphic to an open subset of R. It's connected, so it should have been homeomorphic to an open interval. This is not the case. Why? If these 2 are not homeomorphic, if let's say there is a homeomorphism F between them, let's say this intersection point is X, look at the image of X in the interval, say F of X. If we remove this point, assuming F is a homeomorphism, the restriction to the complement of X should give us a homeomorphism on the complement. This follows from kind of standard points of topology. However, if we remove X, we get 4 connected components in the domain, right? 4 pieces. And in the target, if we remove f of x, we get 2 connected components. However, the number of connected components is a topological invariant. If we had a homeomorphism, these two numbers should have been equal. They are not. Therefore, these two things are not homeomorphic. So X does not have any small neighborhood which looks like an open subset of R. We can see the same thing for this cone. So if you look at the intersection point, the essential part is that these two things are not homeomorphic. If you look at the intersection point, look at its image in the open disk, if there was homeomorphism. If I remove the point from the domain, I get two connected components. If I remove the point from any open subset in R2, I still would have just one connected component, right? Again, the number of connected components should be a topological invariant. This means these two are not homeomorphic. So cone is also not a manifold. Okay. Now, when we have some manifolds, using them, we can construct new manifolds. For instance, through product of smooth manifolds, we can get new manifolds. So product of smooth manifolds can be equipped with a manifold structure. Let's say M1 and M2 are two smooth manifolds. So M1 has some open sets U alpha and some maps phi alpha. M2 has some open sets V beta and maps psi beta. The claim is that M1, let's say M1 is n-dimensional and M2 is m-dimensional. We denote the dimensions like this. The claim is that the product would have a manifold structure, which would be n plus m dimensional. How would that work? So I should cover, well, we first equip it with product topology. So the open sets would be U alpha times V beta. And the maps we construct on these U alpha V beta to open subsets of Rn times Rm, which is Rn plus m, are just by coupling phi alpha and psi beta. These would be the maps, kind of the homeomorphisms to open subsets of the Euclidean space we construct. How does this map work? Well, take any point xy in the product. Phi alpha psi beta would send it to phi alpha x, which is defined, and sub beta y, which is also defined. One can check like these maps whenever we have non-trivial intersections between open subsets covering M1 times M2, they give us kind of smooth maps on Rn plus m. So let's look at two examples of manifolds we studied. One is n-sphere Sn. This essentially means the set of points in Rn plus 1, say x1 up to xn plus 1, where x1 squared plus up to xn plus 1 squared equals 1. This is a subset of Rn plus 1. So S1 is a subset of R2, it's the circle. S2 is a subset of R3, is the sphere, or 2 sphere. So S2 sits inside R3, etc. And then the other example is n torus, denoted by Tn. This is defined to be product of S1 n times. We denote it by Tn. It's an n-dimensional manifold following the product kind of setup we had. So when n is equal to 1, we get again circle. So T1 is the same as S1. When n is equal to, we can actually get in the case n equals to 2, we get the kind of surface of donut. To see this, think about S1 times S1. Circle is like an interval where the endpoints are glued together or identified. So S1 is the same as interval where these two red points are identified. So we have another copy of S1 in S1 times S1. Let's say this is the other S1 component, and there also the blue points should be identified. So the product would be something like the square, but these kind of red points 2 by 2 should be identified. This implies the whole left side should be identified or glued to the right side. And the whole kind of bottom side and top side should be glued together. So let's show they are also identified. Okay, what would happen if I do that? What if I get the square and glue the red sides and blue sides? What would be the result? Well, let's glue the red sides. I would get a cylinder, right? Let's say it's glued along this red segment. Now let's glue these two blue sides. what would happen? What would be the resulting object? It would be just the surface of a donut, right? This is the two torus, or simply torus. So there would be a red segment here and blue one. This is kind of the resulting object. Okay, this seems like a good place to stop. We continue with the next